NASA says its Voyager 1 probe, the most distant human-made object in the universe, is still sending usable information to Earth. Launched in 1977, Voyager 1 has been making headlines for over 45 years, revealing shocking and unexpected secrets from interstellar space. Not only did NASA use the spacecraft to discover a massive storm on Jupiter and rings around Saturn just a few years after its launch, but Voyager 1 has also recently made a strange and seemingly impossible discovery that has scientists confused and concerned. The issue arises from the system controlling Voyager 1's operations, as its data does not align with the spacecraft's current activities. This discovery has sparked curiosity about the nature of the problem and what it could mean for the future of space exploration. Despite being 15 billion miles away, Voyager 1 continues to function well, receiving commands from NASA, carrying them out, and transmitting scientific data back to Earth. However, there's a troubling issue with one of its key systems, the Attitude Articulation and Control System, AACS, which maintains the spacecraft's orientation in space. The AACS ensures the probe's high-gain antenna remains pointed towards Earth to send data, but the data it sends back doesn't match what Voyager 1 is actually doing. This inconsistency, while not immediately dangerous, is enough to cause concern. Due to Voyager's distance in interstellar space, it takes over 20 hours for a signal to travel one way, meaning any communication takes more than 41 hours round-trip. Despite this delay, the team has determined that the AACS is likely still working, but its irregular data readouts haven't yet triggered a protective, safe mode. Intriguingly, the signal from Voyager 1 is as strong as ever, suggesting that the antenna is still properly aimed at Earth. The scientific team is now investigating whether the AACS is generating erroneous data or if another system is causing the issue. Until they understand the problem, they cannot predict whether it will impact Voyager's ability to collect and transmit scientific data. In a 2022 release, Suzanne Dodd, project manager for both Voyager 1 and 2 at NASA's Jet Propulsion Laboratory, acknowledged that these kinds of mysteries are expected at this stage of the mission. She noted that Voyager 1, now nearly 45 years old, has far outlasted initial expectations and is exploring interstellar space, a region filled with high radiation where no spacecraft has ever traveled. This presents significant challenges for the engineering team, but Dodd remains optimistic that they will find a solution. If the team cannot determine the cause of the issue, they may need to adapt by using backup hardware systems or altering the software. Voyager has successfully relied on backup systems in the past, such as in 2017 when it used thrusters that had been inactive for 37 years. However, the spacecraft is old and generates very little power each year, which has led to the shutdown of many subsystems and heaters to conserve energy for the most critical operations. Despite Voyager 1's current issues, its journey has been filled with historical achievements. One of its most notable stops was at Jupiter in 1979, where it made groundbreaking discoveries. Voyager 1 found that Jupiter has a ring system, which was a surprise at the time since scientists thought only Saturn had rings. These faint rings, made mostly of dust particles, were captured in stunning detail by Voyager 1. The spacecraft also provided valuable insights into Jupiter's Great Red Spot, a massive storm larger than Earth that has been raging for at least 400 years. Voyager 1's images of the storm helped scientists better understand its structure, revealing strong winds moving in opposite directions around its center. Voyager 1's discoveries continued when it arrived at Saturn in 1980, where it found new moons and studied the planet's complex ring system. Before Voyager 1's flyby, Saturn's rings were known, but the spacecraft provided close-up views that revealed the rings were made of countless particles ranging from grains to boulders. These particles orbit Saturn in an intricate system of rings, gaps, and divisions shaped by gravitational interactions with the planet's moons. Voyager 1's study of Saturn's largest moon, Titan, also gave us crucial geological insights into the moon's origins and evolution. Voyager 1 didn't stop at observing Jupiter and Saturn. It also examined their moons, including Europa and Enceladus, where scientists believe there may be hidden oceans beneath their icy surfaces. Europa, one of Jupiter's biggest moons, has long been a focus of interest because its cracked and ridged surface suggests tectonic activity, which might point to a massive ocean beneath the ice. This discovery excites scientists, as liquid water is essential for life. raising the possibility of life forms existing beneath Europa's icy crust. Similarly, Saturn's moon Enceladus also has a subsurface ocean. The Cassini spacecraft detected water vapor jets shooting out from the moon, along with organic molecules, which are the building blocks of life. This discovery has further fueled the possibility of life beyond Earth. Both Europa and Enceladus are now seen as potential hotspots for future exploration, with NASA planning missions like the Europa Clipper to study these moons and their hidden oceans. More missions are underway to reveal what's really going on with Jupiter and Saturn's moons. Voyager 1 has discovered significant information about these planets, but it's clear that the spacecraft is only just beginning to unveil their secrets. NASA has released more details about shocking discoveries related to the two gas giants. Voyager 1's journey into space remains unstoppable as it continues to push through the vast emptiness of space. Meanwhile, Voyager 2, the twin spacecraft of Voyager 1, is also performing well in interstellar space. It is currently about 12.1 billion miles, or 19.5 billion kilometers, away from Earth. To put that in perspective, the farthest planet from Earth, Neptune, is only 2.9 billion miles away. Both Voyager 1 and Voyager 2 were launched in 1977, far exceeding their initial mission of flying by planets. Today, they are the only spacecraft collecting data from interstellar space, providing valuable information about the heliosphere, a bubble created by the sun that stretches beyond the planets in our solar system. This data is helping scientists better understand this distant and largely unexplored region of space. Speaking of Voyager 2, it has made groundbreaking discoveries since it entered interstellar space. On November 5, 2018, Voyager 2 became the second human-made object to enter this region. Scientists have since shared the first significant scientific data from this event. Despite crossing the boundary of the heliosphere, the probes haven't yet exited the solar system. The true edge of the solar system is at the farthest part of the Oort cloud, a region of small objects influenced by the sun's gravity. It's estimated that Voyager would take about 2,300 years to reach the inner edge of the Oort cloud and about 30,000 years to pass through it completely. On November 4, 2019, 5 studies were published in the journal Nature Astronomy detailing Voyager 2's findings. There is a boundary where the hot solar wind from the sun meets the cold interstellar space, known as the heliopause. Data from Voyager 2's instruments confirmed that the spacecraft crossed this boundary on November 5. On that day, solar wind particles around Voyager 2 significantly decreased, indicating its exit from the heliosphere. As Voyager 2 moved past the heliopause, it transitioned from the hot, less dense plasma of the solar wind into the cooler, denser plasma of interstellar space. This discovery indicates a balance between these two regions, and scientists believe that the density helps even out pressure differences. Voyager 1 had previously entered interstellar space in 2012, but its plasma instrument was damaged, preventing the collection of complete data during its crossing. However, data from both Voyager 1 and Voyager 2 has revealed that particles from the solar wind and the interstellar wind mix and spill across the boundary. The interstellar wind, created by stars that exploded as supernovas millions of years ago, plays a crucial role in defining the boundary between the heliosphere and interstellar space. Voyager 2's crossing helped astronomers discover that the heliosphere has a smooth but clear boundary between different types of plasma. Additionally, Voyager 2 detected a solid interstellar magnetic field, which was stronger than what Voyager 1 had measured. This magnetic field originates from exploded stars, which send out material and their magnetic fields into space. The way the sun interacts with interstellar space is a subject of great interest for scientists. When the sun releases shock waves, they travel through the heliopause and into the interstellar medium, causing disruptions, much like how shock waves from supernovas move through the space between stars. The early data from Voyager 2's crossing is helping scientists build a more detailed picture of what happens in the space between the sun and the interstellar medium. This information is valuable because other stars are likely to exhibit similar characteristics. As astronomers study stars with planets around them, they can use what they've learned from Voyager 2 to better understand other star systems. By comparing Voyager 2's findings with Voyager 1's data, scientists can identify both similarities and differences. These two data points are crucial but scientists hope for another interstellar probe from NASA to gather even more information. The heliosphere can be thought of as a windsock, with astronomers wanting a probe that can travel along the tail created by the sun's wind, extending the solar system's boundary. This would allow for the collection of additional data on the heliosphere and its interaction with interstellar space. Voyager 2 has also made discoveries related to Jupiter's moons, similar to Voyager 1. In 1979, Voyager 2 observed a small moon called Adrastea orbiting Jupiter. This was a significant discovery because it was the first time a moon was detected using images from a spacecraft in space, not just from a telescope on Earth. Adrastea was named after a figure from Greek mythology and is unique because it orbits Jupiter in less time than the planet takes to rotate. It is located on the edge of Jupiter's main ring, and scientists believe it may be the primary source of material for these rings. However, despite observations from the Galileo spacecraft in the 1990s, we still know very little about Adrastea's composition and appearance. David Jitt and Edward Danielson were the scientists who discovered Adrastea while analyzing photos taken by Voyager 2 on July 8, 1979. In those images, Adrastea appeared as a tiny dot. It wasn't until 1998 that we began to understand its shape more clearly, thanks to images from the Galileo spacecraft, though the photos were not highly detailed. Adrastea was officially named in 1983, after a nymph from Greek mythology who cared for Zeus, the Greek equivalent of Jupiter in Roman mythology. In 2016, another spacecraft, Juno, reached Jupiter. While its primary mission is to study Jupiter, it may still capture images of Adrastea and other moons, though they are likely to be less detailed. Adrastea is the smallest and second closest of Jupiter's inner moons, orbiting the planet at a distance of about 129,000 kilometers, which is roughly 1.86 times Jupiter's diameter. It lies on the outer edge of Jupiter's main ring, and its orbit around Jupiter is relatively stable, with only minor eccentricity and tilt relative to Jupiter's equator. Adrastea's orbit is smaller than Jupiter's synchronous orbit radius, meaning that over time, its orbit will gradually shrink and may eventually lead to a collision with Jupiter. However, since Adrastea hasn't yet disintegrated, its orbit must be further away than initially thought. Both Voyager 1 and 2 were originally expected to last only 5 years, but remarkably, they have been operational for 42 years. This longevity is a testament to the engineers who have worked to keep these twin spacecraft running. Now, a new plan has been developed to extend the operational life of both Voyagers, allowing scientists to continue receiving crucial data from the unexplored regions of space. One of the key challenges is ensuring that the spacecraft have enough power to keep their scientific instruments functioning.